Hello, I'm Seema and welcome to part 26 and the last part of the chapter, Solutions. In this video, I'm going to solve two solved examples and I'm just going to explain them to you based on abnormal molar masses. And I hope with the help of that information or with that understanding, you would be well equipped to solve as many problems as you can on your own. So not wasting any time, let us start with the first problem. The question reads, this is question 2.12, and the question reads 2 grams of benzoic acid dissolved in 25 grams of benzene shows a depression in freezing point of 1.62 Kelvin. Kf for benzene is given, which is equal to 4.9 Kelvin kg per mole. What is the percentage association of acid if it forms a dimer in solution? You're supposed to find out the percentage association. But we come to this later because we have to first find out the want-off factor. And in order to do that, we must know the molar mass of the solute. So what is the information that we have? Let us first write that down. Benzoic acid is dissolved in benzene. It means benzoic acid is the solute. So the mass of solute is W2 is equal to 2 grams. And the solvent is benzene. So W1 is 25 grams. Right? And it shows a molar depression in freezing point, that is delta TF is equal to 1.62 Kelvin, right? And Kf is given to you, which is equal to 4.9 Kelvin kg per mole. Now this is the information that is given to us, right? We know that delta TF is equal to Kf into small m, where small m stands for molality. Now, what is molality? Molality is defined as the number of moles of solute present per kg of the solvent. And how do you calculate the number of moles of anything? The number of moles of anything is the mass upon the molar mass. So, to find out the number of moles of solute, we need to know the mass of the solute, which is W2, upon molar mass of the solute, which will be M2. Now this is the number of moles of solute present into Kf, of course. Kf into W2 upon M2. And divided by the mass of the solvent. Mass of the solvent is 25 grams, which is W1. But we want the mass of the solvent in kgs. In order to convert the grams into kgs, if this is in grams, to convert it into kgs, you divide it by 1000 grams per kg. So this is the formula that you would get. Now we need to find out the molar mass because we have the value of delta TF. So let us exchange these two. So what is the formula for molar mass that we get? Molar mass of the solute, that is M2, would become equal to Kf into W2 into 1000 grams per kg upon the M2 is substituted with delta TF now. It comes down here into W1 in grams. I'm not writing the unit here because it's understood it's in grams. That's why we had to multiply it by 1000. Let us now substitute all these values to calculate M2. So M2 becomes equal to, what's the value of Kf? Kf is 4.9 Kelvin kg per mole. Right? And into, what is W2? It is 2 grams. Into 1000 grams per kg. Divided by, in the denominator, what do we have? Delta TF. What's the value of delta TF? 1.62 Kelvin. And it is 1.62 Kelvin into, what is the mass of the solvent? W1 is 25 grams, right? When you solve all of this, you will get the molar mass in grams per mole. And how much would that be? That would be 241.98. 241.98 grams per mole is the molar mass. Now you have calculated the molar mass of the solute. After knowing the molar mass, in order to really know the percentage association, what is it that is happening to the solute? You had, let us say, 2 moles of benzoic acid, that is C6H5COOH. It dimerizes to give you C6H5COOH whole twice, right? But in your final solution, what do you have? Let us assume that X amount of it dissociated, or rather associated. If you had 2 moles or whatever was the initial number of moles, out of that amount, X amount or 1 whole, whatever that 1 whole was, out of it, X amount got dissociated, so 1 got associated. So after association, how much of it has remained if you started with 1 mole and X amount, X number of moles they associated, the fraction. Then you would be left with 1 minus X of benzoic acid in the unassociated form. And what is the associated form then? You have, if there was X moles, we know 2 molecules make 1 dimer. So if you have X molecules, how many dimers will be formed? X by 2, right? So once the solution is made, what is the total number of moles of the solute that you have? Now the total number of moles of solute in the associated and the unassociated form are these. Therefore, the total number of molecules of the total number of moles, total moles of solute. Now this 2 does not mean that there are 2 moles of it. We're just talking of 1 whole. The 2 has been put, let us say this is a molecular equation to explain what is the ratio. That's not the actual concentration. So total number of moles of solute according to this would be 1 minus X plus X by 2. Now minus X plus half of X would be minus X by 2. Therefore this would be equal to 1 minus X by 2. I hope I'm clear. So this would be 1 minus X by 2. Now this is the number of moles of the solution that of the solute that we have in the solution. Now this is the want-of factor. Because what is want-of factor? Want-of factor is actually the number of moles of solute which is present in the solution. Therefore, if you really look at this, this is want-of factor which is equal to I. So, I is equal to 1 minus X by 2. But how do we define want-of factor? Want-of factor is equal to the normal molar mass upon the abnormal molar mass. Right? Want-of factor is normal molar mass upon abnormal molar mass. What is the abnormal molar mass? The mass that we calculated here is the abnormal molar mass. The one that we calculated from this equation was the abnormal molar mass. And what is the normal molar mass of the solute? And what is the solute that you have? Benzoic acid. The normal molar benzoic acid, the formula is C6H5COOH. What would be the mass? There are 7 carbons. The mass of 1 carbon is 12 into 7 plus 2 hydrogens are 6. The mass of 1 hydrogen is 1 into 6 plus oxygens are 2. The mass of 1 oxygen is 16 into 2. And when you calculate this, the molar mass of C6H5COOH, that is benzoic acid, comes out to be 122 grams per mole. And what is the molar mass that we have calculated? We've calculated 241. Let me just verify. Yes, it is 122 grams per mole. And what we calculated was 241.98. So this becomes, which means that this becomes equal to I, or want-of factor becomes 1 minus X by 2 is equal to, normal molar mass is 122 grams per mole upon the calculated molar mass, which is 241.98 grams per mole. Do you get this? Now from this we would like to calculate X, where X is the degree of association. If you have the degree of association from 1 whole of the solution, that if the solution was 1, this is the degree of association. Once you know the degree of association out of 1, can you not calculate it out of 100? If out of 1 this much has associated, then out of 100 you will multiply it by 100 to get the percentage. So that is what we want to do. We want to know the percentage association. So we must first know the degree of association, which is x. So from this we will get x by 2 is equal to 1 minus 122 upon 241.98 gram per mole is cancelled here, right? And whatever this is, if you want to find out x, then you will multiply this by 2. And when you do so, what do you get? You get the answer will be 0.496 into 2. 0.496 into 2, this would be 0.496, and into 2, which would give you 0.992. 0.992. 0.992 is the part of out of 1 whole which associated. So out of 100, it would be into 100 to get the percentage association. You will get 0.992 into 100, which is equal to 99.2%. So that is the percentage of association, right? Now give me a moment to write down one last problem. Let us now solve the next question. This is question 2.13. Let me read the question first. 0.6 milliliters of acetic acid having a density of 1.06 grams per ml. Look, volume and density are given to you. Mass is equal to, or what is density? Density is mass per unit volume. Mass is not given, volume and density are given. Just a trick to make you calculate even the mass. So 0.6 ml of acetic acid having a density of 1.06 grams per ml is dissolved in 1 liter of water. The depression and freezing point observed for this strength of acid was 0.0205 degrees Celsius. Again, a trick here. The difference in temperature, whether it is in Celsius or Kelvin, the value of the degree is the same. So you need delta TF to be in Kelvin. But they've given it to you in Celsius. So Celsius, the numerical value will remain the same. You'll change the unit to Kelvin. You have to calculate the want-off factor I and the dissociation constant, which is Ka. We've studied equilibrium, and what is dissociation constant Ka? It is the concentrations of the products divided by the concentration of the reactant for weak electrolytes. I'll come to that later. I used the table to find out the value of Kf already. That is the value of Kf for acetic acid. So now, how do we go about this problem? You have been given 0.6 ml. So first thing is you must know the molar mass of acetic acid, right? CH3COOH, or let me first write down what all have we been given. We've been given CH3COH having density is dissolved in, so this is the solute. Solute is always 2. So V2, volume 2 is given to us, which is 0.6 ml. D2 density is given to us, which is 1.06 grams per ml. So you've been given how many mLs are there and what is the mass of 1 ml. So you can calculate the mass of these many milliliters. That will give you the mass of the solute. That is acetic acid. And you need to find out the molar mass of the acetic acid to calculate the number of moles of acetic acid. So to calculate number of moles is mass over molar mass. What is molar mass of acetic acid? CH3COOH. So M2 would be equal to CH3COOH. Carbon is 12, hydrogen is, and how many carbons are there? There are 2 carbons plus 4 hydrogens. Mass of 1 hydrogen is 1, and there are 4 hydrogens plus there are 2 oxygens, so 16 into 2. When you calculate this, this comes out to be 60 grams per mole, right? And what else is given to us? The depression and freezing point observed for the strength of acid, that is delta TF. That was observed, so this is the observed value. Why am I writing this? Because what is want-off factor? Want-off factor is observed colligative property upon the calculated colligative property, right? Yes. So it would be the observed colligative property upon the calculated colligative property. Therefore, I am writing observed here. And what is the value of delta TF that is given? 0.0205 degrees Celsius can be written as Kelvin. I told you just now that the value is the same of 1 degree is the same. You have to calculate I is to be calculated, and you have to calculate Ka. These are the two things that are to be calculated. In order to know the number of moles, now what is delta TF? Delta TF is equal to Kf into m. Now how do you calculate molality? Molality is the number of moles of the solute upon the mass of the solvent in kgs. In order to come to this first, we need to know the number of moles of solute. And how do you know the number of moles? Number of moles is mass of the solute divided by the molar mass. The molar mass we know is 60 grams. And how would you calculate the mass? You've been given the volume and the density. So the mass over molar mass, or number of moles of solute, that is N2, would be equal to V2 into D2 upon M2, right? Where volume is 0.6 ml into 1.06 grams per milliliters upon 60 grams per mole. And this will give you the number of moles. All units would get cancelled and you'd be getting the number of moles. So number of moles of the solute, when you calculate from this, how much would you get? .0106. Number of moles will be equal to 0.0106 moles of number of moles of the solute, that is acetic acid. Now this is equal to N or N2. So what would molality be? M is number of moles of solute divided by the mass of the solvent in kg. What is the solvent? Solvent is water. And what is the volume of the solvent given to us? 1 liter. We know that 1 liter is 1000 milliliters. And again, we've been given the volume. So for water, 1000 ml is given to us, or 1 liter. And the mass of 1 ml of water is equal to 1 gram. So 1000 ml will be 1000 grams. It means the mass of the solvent is 1000 grams. And in order to convert it into kgs, you will multiply it by 1000 gram per kg, right? Now, substitute the value. What was N2 that you calculated? It was 0.0106 moles into 1000 grams per kg upon 1000 grams. It will be the number of moles per kg. So the 1000 and 1000 will get cancelled, gram and gram will get cancelled, moles per kg, you will get 0.0106 moles per kg, or small m. The unit can also be small m for molality. Now, what is delta TF? Delta TF can now be, this is the observed one. We have to calculate delta TF. The value of Kf I found out from the table, which was equal to Kf into m. Kf is 1.86 Kelvin kg per mole, and m we just calculated is 0.0106 mole per kg, or small m also you can write. Anyway, that will be cancelled out in the end. So delta TF, when you calculate this, would come out to be equal to 0.0197 Kelvin. 0.0197 Kelvin. Now, this is the calculated colligative property, calculated. And what is want of factor? Want-of factor is the observed colligative property. Upon the calculated colligative property, which is equal to, what was the observed colligative property that was given to us? 0.0205 Kelvin divided by 0.0197 Kelvin. And that gives us the value of want-of factor I will come out to be equal to 1.041. 1.041 is the value of want-of factor. Now, we are supposed to find out the value of the dissociation constant. In order to have the value of dissociation constant, we must know how much of it dissociated, because it's a weak electrolyte, and what was the concentration at equilibrium. Again, if you do not remember how this was done, I would encourage you to go to the chapter Equilibrium, which you did last year, and see how you solve the numerical problems. Let us see what happens here. The acetic acid, that is CH3COOH, is a weak acid. It dissociates in solution to give you CH3COO negative plus H positive. Now, let us assume that X amount of this dissociates. If you had one, we begin with N amount or N number of moles. Let us say that X amount dissociated, or X was the degree of dissociation. If it was the degree of dissociation, then you started with one hole and X out of it dissociated. But what is the total number of moles that you have? You have N. Remember, in the previous question also we did this, where I told you the total whole was, we understood N to be 100. That is why we found out the percentage. And we took it as one whole, the solution, the solute, and X dissociated. We are doing the same thing. 1 minus X would remain, but 1 minus X of what? 1 minus X of N. In that case, N was 100, because when we were trying to find out the percentage, that total amount was 100. If out of 1, X dissociated or associated, whatever is happening, in this dissociation is occurring, then that total number there was 100, but here it is N. So based on that, if 1 out of X, 1 minus X dissociated out of a whole, out of N, 1 minus X dissociated, then what would be the concentration at equilibrium or in the solution? It would be NX, and this would also be NX. The concentrations of both CH3COO negative and H positive would be NX and NX. Now, what is the total number of moles of particles present in the solution after dissociation? So this is all in moles, mole, 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 right? So the total number of moles would be N 1 minus X plus NX plus NX. So we can simplify this. This, take N as common, so N 1 minus X, here we are taking N common here, plus X plus X. So minus X and plus X get cancelled, and you get here N 1 plus X. Now this is the total number of moles of the solute present either in the associated or dissociated form after the it is after dissociation. We know that want-of factor also can be stated in terms of the number of moles present after dissociation and before dissociation. So we say want-of factor I can also be written as the want-of factor I can also be written as the number of moles after dissociation upon number of moles before dissociation. We know we started with N number of moles. That was the number of moles of the solute before dissociation. So you get this is equal to N 1 plus X is the number of moles of the particles after dissociation divided by N. So N and N get cancelled. We had also calculated the value of I here. So the value of I now becomes equal to 1 plus X, which is equal to 1.041. from this equation, you can calculate the value of x. So, x becomes equal to 1.041 minus 1, which will be equal to 0.041 is the want-of factor. Now that you've calculated the value of x, in this equation, you're supposed to know the concentrations of all the solutes and the solvents. Now let us calculate the value of Ka. In order to calculate the value of Ka, what is Ka? Ka is equal to the concentration of CH3COO negative into H positive divided by the concentration of CH3COOH, right? Now, which is equal to NX into NX upon N1 minus X. This will give you the value of Ka. But first, let us find out the individual, since we have all these values, let us find out the individual values of these. What will be the concentration of CH3COOH? In order to calculate the concentration of it is N1 minus X. We had calculated the value of N. N was 0.0106. 1 minus X is 0.041. That is the concentration of acetic acid. What is the concentration of CH3COO negative and the concentration of H positive? Both are equal, which is equal to NX, and the value of N is 0.0106 into X is 0.041. So when you put these values in Ka, Ka would be equal to 0.0106 into 0.041 into 0.0106 into 0.041, that is concentrations of both CH3CO negative and H positive, divided by 0.0106 1 minus 0.041. And when you calculate all of this, what do you get? You get 1.86 into 10 to the power minus 5. 1.86 into 10 to the power minus 5 is the value of Ka. Right? And since Ka is only a ratio of all the concentrations, all units would get cancelled out and it has no units. So this was the chapter solutions. With this, I'll end this video. If you found it helpful, give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.